Hello everyone, welcome to another video in the ARM assembly bare metal Raspberry Pi programming series. And it seems like every time I say that, I do it in a different order, but you get the point. So today we're going to go a little off topic. Normally we talk about programming and how the code that you enter gets compiled and what it does. Today we're going to talk about the actual circuit that we're going to be driving in the next video. As you know, we're going to be blinking on and off an LED. Now, to do this, a lot of tutorials, I notice they'll just show you the setup, and I guess they focus only on the programming, and you're supposed to know that that's the way the circuit's supposed to work, and you just proceed forward. However, if you have the wrong size resistor, you could potentially short out the Raspberry Pi and burn it out. Also, avoid static shock with the Raspberry Pi. You could burn it out. And if you have the LED pointing the wrong direction, it won't turn on. So you could think your code's bad, and it's just because your circuit is not configured properly. And obviously, whenever you're dealing with low-level stuff, there's always a risk that something can go wrong, and thus the reason in the description I have the little hold harmless clause. However, you're going to see me doing everything, and therefore if you do things the way I do and they don't burn out, they shouldn't burn out for you either. So it's not like we have to be oversensitive to it, but I guess it's worth mentioning. First of all, let's talk about breadboards. So this is an example of a breadboard. Now this orientation doesn't make sense to me because you can see all the letters are sideways. So I downloaded the picture and I made it bigger and rotated it. Now you see there's a positive, negative, and this is your power rail. This is where your power source will plug into, and when you connect to any one of these holes vertically, all of the other holes vertically will become energized. And you see there's another rail on this side. Are these two connected? No, they are not. Actually, some kits will have 3.3 volts on one rail and 5 volts on the other. A lot of the older chips used 5 volts, thus the reason why we used 9-volt batteries back in the day. And the new ones will often use 3.3 volts because we want to use less watts and have less heat dissipation and all the energy savings stuff. So it's kind of like newer and older technology, I guess, but since there's a lot of carryover components from back in the day, we still work with 5 volts sometimes we work with 3. The Raspberry Pi specifically, we will be working with 3.3 volts. Now, you understand that these are all connected vertically. What about the interior? Well, the interior is actually connected horizontally. Now, all of these holes in this row are connected until you get to the middle point, and then all of these holes are connected. The reason for that is if you put an integrated circuit or a chip on here, you want to be able to access all of the pins, but you don't want to necessarily cross-connect these pins. So that is the reason for that. Now, let's just walk through an example. If you were to take a lead from your power source and put it in the positive, one of these positive holes here, we know all the holes vertically are energized, so we'll grab another one of these holes, run a lead from there to row 2. Now row 2 will be positively energized as well, and you can run resistors and LEDs and various other things off of this row 2 then. And that's really all there is to say about breadboards. You know, if you're wondering what the interior looks like, if we go back to this orientation, another Google image find I found is, here's an example. You can see there's just like a metal foil that connects all of these together. And the benefit of a breadboard, obviously, is you can connect components together without having to solder them together. You don't need to use wire nuts. You don't need to try to hold them together with your fingers. Don't do that one because you don't really want to be involved in a circuit. All right, so that covers the breadboards. Next, well, let's look at our actual circuit. So I drew up a real basic example of the circuit we have. We have positive 3.3 volts, a 5 kilo ohm resistor, an LED, and a ground. Now you'll see that these are connected all in series, so the electricity has one path to go. And if you took a physics class, you know that electrons flow from negative to positive. That's called electron flow. We don't really use that in electronics. We use conventional flow. Conventional flow flows from positive to negative. And a way that you can remember that things are oriented the right way is, for instance, diodes. When you look at conventional flow, obviously, positive to negative, the way the arrow points is the way the electricity is allowed to go through the diode. Now, there are special purpose diodes, like Zener diodes, that work a little bit differently or unusually compared to this, but we're working with an LED, so we're not going to get into those special use case scenarios. All right, so we start with positive 3.3 volts off of the Raspberry Pi. We go through the resistor, through the diode, over to ground. 5.5 kilo ohms. Why did I choose that number? Well, I reached into my box of diodes are in there too. My box of resistors, and I pulled this one out, and I knew it was going to be large enough. So, what do I mean by large enough? Well, if we go to Stack Exchange, we can see that other people have researched this, and the maximum draw you should have on a single pin is 16 milliamps. You do not want to exceed that. So obviously by adding a resistor, we reduce the amperage because it resists the flow. Now the equation that we use is voltage equals current times resistance. Let's write this out. I think T is the right one. So voltage equals current times resistance. We can change this by dividing I out of both sides. So we take our voltage, which is 3.3 volts, divide it by the current, which is going to be 0.016 because it's 16 milliamps. And doing that math, we get 206 ohms is our minimum. Well, actually, let's think about that real quick, because the 16 milliamps is for the Raspberry Pi itself, but have we considered the LED? No, we haven't. Let's look into that real quick. So, okay, and all right. Yes, so let me bring this over. You can see that in LED, now that granted they have different voltages they're working with here, but they do specify that we might want to be aware of 10 milliamps. So as opposed to the 16 we were looking at before, if we take 3.3 divided by 0.01, that will give us a resistor minimum of 330 as opposed to the 206 that we were looking at before. Well, that's good to know. So we just saved you from potentially burning out an LED. That's good. As you can see, I erred on the side of caution with my calculations. So, yeah, I would recommend going for a slightly larger resistor. So I have 5 kilo ohms. I'm definitely on the safe side of that. Now let's talk about the LEDs a little bit. When you look at an LED, they will have a long leg and a short leg. The long leg goes to the positive side and the short leg goes to the negative side. If you were to hook it up backwards, it would be the same as doing this, and then obviously this is not the way the electricity wants to flow, and therefore our LED will never light up. Now, how can you remember that the long leg goes to the positive side and the short leg goes to the negative side? The way I remember it is plus is larger than minus. Positive numbers are larger than negative numbers. So the plus side or the longer side of the LED, the two of them go together, and the short side goes to the negative or the ground. Is that the best way of remembering it? I don't know, but it works for me, and maybe it'll work for you. All right, so let's cut over to real life and show you on an actual breadboard what this circuit will look like. All right, so we have our breadboard here, and as you can see, there are two leads going into our power rails. I have red going in the positive and brown going in the negative. I guess red is kind of like hot and brown is the color of the dirt on the ground, I guess. These are by no means official coloring schemes at all, and the reason I chose them was because they were stuck together from the factory with just the way that they formed it. You can see that they are going to the GPIO. They're in the bottommost area. We'll talk about that in the next video. For this video, let's focus in on this circuit. So the resistor, one leg goes into the positive power rail, and that will bring power over into this row. And you can see that the LED is also in the same row. The power will then continue to flow down into the negative side. Let's look at this LED here. You can see, well, if I straighten the legs out, you can see one leg is longer than the other, and just like we mentioned before, the longer leg goes to the positive side. Now there's supposed to also be a little notch, and you can't really see it on this inexpensive LED, but the notch is on the negative side. Some of them it's more evident, and the camera is just going wild trying to focus on this stuff. But so you can remember that not only is the leg shorter on the negative side, but it's also missing a little hunk of plastic on the rim that unfortunately is not very visible. Oh, there, it's finally in focus. Well, anyway, for what it's worth, that is our circuit. So just remember the longer leg goes to the positive side. All right, so we have explained a little bit about breadboards, why we have a resistor. We also talked about the sizing of the resistor. We talked about the diode with the conventional flow versus electron flow, and we talked about the proper orientation. And we are now ready. We are now ready. In the next video, we will actually be able to do the blink test with the LED. So that's very exciting. I look forward to seeing you in the next video, and if you've stuck around this long, please do also consider subscribing to the channel. It does help the channel. So until next time, keep on programming.